All right, let's start. All right, so today's lecture is about convolutional neural networks. In the grand scheme of things, of which we had this slide, the previous to last time, we now arrived at this part. And lucky for you, we've done these parts already. So really good stuff. And so let's start with a quick recap of the MLP, the multi-layer perceptron. We've sort of had this in the second lecture where we discovered that the MLP just scales really badly. You need millions of parameters even if you just want to have a single hidden layer, and a single hidden layer doesn't make your neural network very nonlinear. If you have, for example, ReLU units, that barely adds any nonlinearity, so you're like slightly better compared to a linear model. So judging from this basic multi-layer perceptron setup, we want to start with this and think about it in a bit more detail. So if it's not so good, coming from last week's lecture, can we think of ways how to regularize this fully connected layer? For example, by adding some sort of sharing between the weights. So can we say these neurons share their matrices, for example? If you think of a single fully connected layer being just a matrix, can we say, okay, these should be the same for particular neurons? Or can we add some prior knowledge into these weights? Fully connected layers, they say everything is connected with everything else. There's no inductive biases. So inductive bias simply means there's no prior knowledge baked into this. So a fully connected layer could do anything. Yeah? Yeah? Louder volume? Yes. Can do. Test. Better? Yeah? Okay. Okay. This should be good, hopefully. All right. So we have this basic idea, and we're going to see how we can use it for how that basically directly leads to convolutional neural networks today. We start off with a very, very basic idea. So some of the patterns, they're obviously smaller than a whole image. For example, a beak detector that simply detects a beak. And the idea is, okay, can we, instead of having a whole model which tries to find this beak, can we have small models which take a look at this and simply look at this small region and therefore use a lot less parameters? And actually you have this is exactly what has been observed in some animals as well. For example, Barlow detected in frogs, they have basically what amounts to fly detectors. And they are very small units. They have exactly this on and off behavior for a particular neuron, when they see, for example, flies. And so from this basic idea, let's look at, okay, a model which takes a small input and tries to detect whether there's a beak. That was the basic premise. Another motivation, and now we come a bit more closer to how our visual system also works, is the following. For this, I'm going to show you a video, which I hope it will project the audio, but otherwise you can probably hear it as well.
The researchers actually listened in to individual nerve cells firing in the anesthetized cat as they presented it with different visual images.
When we started working, Torsten and I, in the late 50s, we set up our first experiments, and they didn't go well because at the beginning we couldn't make the cells fire at all. We'd shine lights all over the screen and nothing seemed to work. And rather by accident, one day we were shining small spots, either white spots or black spots, onto the screen, and we found that the black dot seemed to be working in a way that at first we couldn't understand until we found that it was the process of slipping the piece of glass into the projector, which swept a line, a very faint, precise, narrow line across the retina. And every time we did that, we'd get a response.
All right. So a couple of things here. What you heard are the neurons firing in this cat. So you can see they basically put an electrode in the cat's brain, and that's how they measured. Every time a neuron would fire, they would hear this. So this loud noise was multiple of these, which basically meant, okay, multiple, or this neuron is firing. And in animals, humans included, the way a neuron fires is it fires multiple times. In neural networks, you typically have larger activations, but in neural networks, you don't have this time dimension. So that's a major difference, of course, that we always need to keep in mind when we talk about neural networks. They're just inspired by real neural networks. As it so happens, Hubel and Wiesel, which were researchers which worked for a long time together, they actually won the Nobel Prize for something else, where they discovered that there's a critical period for children where the visual develops, where the visual system develops, and if your vision is impaired during that time, it cannot recover. So they basically, this led to the discovery that if infants have cataracts, so if they cannot see very well, that you should operate on that very early on, so the visual system fully develops, and you shouldn't wait until they're adults. And this is quite a thing. Now, regarding this experiment, what you saw is that these neurons were firing not actually at the dot, but rather at the sliding of the panel. So they were reacting to this, well, of the sliding of the panel. The only thing you saw was basically this edge of the panel. So this led to the finding that actually what you have in the brain, and has been replicated multiple times, are at the very basic level edge detectors. Not only any edge detectors, but actually oriented edge detectors. So some neurons might fire to this particular kind of edge, some neurons, and they won't fire if you give it an edge which is oriented orthogonally, for example. They won't fire at all to these. So these edge detectors are orientation specific. I'm not going to go into too much detail of this, but later on they found even more specific neurons. So not neurons that react to specific edges, but neurons which react to specific people or concepts. These were then called the grandmother cells, because you could show a picture of a grandmother, you could tell them grandmother, or you could write out grandmother, and every time that particular neuron would react. We do find something similar in neural networks as well, which is quite funny, but we're not going to dive too much into that. We are taking this edge detector discovery. This was a major thing, or also motivated these edge filters for computer vision as well. And we can see that neural networks, when we train them from scratch on image data, they sort of recover these edge detectors as well. So edge detectors, we can simply use some mathematics to describe them. So for example, Gabo filters, they're not learned filters, they're simply edge detectors. Right, we had these points. Other handcrafted filters include Canny and Gabo filters, which you probably have heard about in Computer Vision 1. They're simply filters where people have thought this is probably important if you want to do visual recognition. But they were sort of handcrafted and a bit hand-wavy. So the major learning is, can we instead also learn these filters? These filters are essentially feature extractors. So you get an image, and these filters extract the important features. So the idea is now, instead of using these extracted features, can we directly operate on the input and let the feature extraction stage also be learned using neural networks? So these were the questions. And this is the point I just mentioned. So RED is the traditional machine learning approach, or the stuff that had been done previously with Hawk, SIFT, or Canny features. And then you had some sort of very easy machine learning model, like a SVM, or even a linear layer or something like that, and it would do classification. Now a neural network, or CNN especially, will be learning these features, will be including this feature learning stage into the learning. So in a way, it takes this machine learning step one step further to the data side. All right, so let's talk about the CNN. Now, convolution might sound difficult, but it's really not. It's just this ocean end of a word, I think. So there's a couple of words like that are really complicated or even dangerous, like think of absolution, revolution, devolution, diminution, like they are all bad words, but convolution shouldn't be one of them. So that it's really simple. So if you have a signal and you have a weighting function Wt, a convolution is simply defined by the following. An integral which sort of slides over this signal xt and computes how much area is under the curve. That's what an integral does. We refer to W typically as a filter or kernel for reasons that you will know in a bit. And we typically write this just simply as the following. You have this sort of star operation. Sometimes the star operation is also used for multiplication, so you need to be a bit careful about what context you're talking about. But in the topic of convolutions, this is the standard. Let's look at what happens if the signal is 1D and the filter is also 1D. It looks as follows. So in blue, you have this curve, you have this function, and now this filter is applied. The filter is simply this rectangle, and you slide this over this function. And now what you can see being plotted in black is simply the area that is under both of these, that's overlapping. So you can see it start off at 0, and then where there's overlapping, this yellow area, that's what's being plotted, and you get this sort of plot at the end. This is what a convolution does. It simply slides one function across another. Now for 2D images, you simply generalize this. And note that here I've gone from the continuous writing to discrete sums, which is the case because now we have pixels. Actually, you can write this in a different way because it's commutative. So you can, instead of summing across mn and I minus m and j minus n, you can simply switch this. This is the same result. And actually neural networks, because of, or neural network libraries, I should say, they actually do something called cross-correlation, which is the same except that the filter is actually flipped horizontally and vertically. But that's just a way how it's implemented. So this is not particularly important. The important part is what it does, essentially. So here you have the broad overview. So you have the input, and you have, for example, the input now consists of pixels. So the pixels are from A to L, A, B, C, D, E, F, G, and so on. And now this kernel, or this filter, has these 4 weights. And so the first output is by basically laying this kernel on top of the input and simply adding the stuff. So A gets multiplied by W, B gets multiplied by X, and so on, and they're simply summed together. They are always summed together because that's what the convolution operation told us, right? And then you take this kernel and you move it one to the left, one to the right, and one to the right, and then you move it to the bottom, and you keep going, and that's what you get as an output. And we'll go back to this in a bit more visual way later on. Let's take a look at these filters. So these filters can do a couple of things already. So for example, even if we just have a 3x3 filter, we can blur images or we can sharpen images. Also have a think about why, for example, the top image blurs. You can also make them detect edges. And for example, you can also make them detect oriented edges as a Sobel filter. For example, in the Sobel filter, you can see that the left side of this weight matrix has positive values, the right side negative values. So if you now slide this across an edge, you will find that it reacts most strongly to vertical edges and basically highlights these. And if the underlying input, for example, is continuous, so all the values in the image are the same, like the background, this will simply cancel out, right? Because you have this linear combination of positives and of negatives, so it will simply give you 0. So it won't react to uniform background, but only react to certain kinds of edges. Now, here's a quick quiz which sort of fits to the random initialization part we had the last 2 times. What is the effect of running a normal randomly distributed, randomly initialized convolution on an image? What happens if you simply do that? A convolution which hasn't been trained, it's simply initialized. And a hint is that if you think about first a very simple 1D convolution that doesn't operate on an image, but instead just on a line. So will it A, emphasize average colored regions, B, emphasize edges, 3, blur the image, or 4, sharpen the image. And this time there is actually one correct answer. All right, let's see what we get. So on the count of 3, 1, 2, 3. So 1, 3, 3, 3, 3, 3, 3, 2, 3. All right. Right. It will actually emphasize edges. It will obviously not keep the image structure perfectly, so blurring is not too bad. But importantly, and perhaps somewhat surprisingly, it will emphasize edges actually. Let's see. So if you think of a random filter, let's say in 2D, which looks like the following, AB, right? You're simply slipping that across. You can rewrite this actually as A, minus A, plus another filter, which is, 0, B plus A. Now, if it's randomly initialized, this is on average This is on average 0, and what you have here is a simple edge detector. Because this one will highlight, again, on an average region, this one will simply zero it out. But if you have an edge, this will highlight the edge. This will only fire if, for example, you have a 1 here and a 0 here, which is exactly what you have in a horizontal edge, for example. And the good thing about this one is that this is exactly how a randomly initialized neural network starts. So it starts actually by looking at edges. And the blurring is also true, like, yes, because it depends a bit on the filter size. Like, if the filter size is huge, and then, yeah, all these values are non-zero, so it will also blur the image. But yeah. Yes?
So just so that
yeah.
it's clear, so normal randomly initialized convolution would imply that each element is IID from a normal distribution?
Yeah. That's what I mean here, at least, yeah.
And so then, in this AB example, the expectation is that A and B would be the same, which is the mean.
In the expectation, yeah, that is true.
Okay, so in the expectation it would blur the image, but if they are different, then it would sharpen edges.
They would sharpen images if they're...
Oh, sorry, not sharpen, but emphasize edges.
Yeah. Yes. And actually, I mean, you can try this out. It's fairly like fun. It won't always work. Like it isn't 100% clear, 100% true. But on average, a couple of filters will be pretty much looking like edge filters. I should say that. Yeah. It's not a clear thing. It's not a fixed random edge detector. But this is a reason why randomly initialized neural networks are not that bad, because they focus on edges already. There's a couple more reasons why convolutions are good. So for example, if we want to detect dogs in the top left corner or in the bottom right corner, we simply don't want to be learning different kinds of modules in our neural network. We want this to be instead one detector which works across the whole image. So what we mean here is that this receptive field of a neuron, has a small receptive field, but you can work this across the whole image. You have the parameter sharing aspect, so simply you save parameters. That's simple enough. And you have this equivariant representation. Not only do you save parameters, but also no matter if you have a dog at the top left corner or at the bottom right corner, you get the same features out. You get the same activations out, which is very useful. Let's go through these motivations one by one. So about the sparse connection. On the right-hand side, you can see a fully connected layer. So you can see we're focusing on the middle neuron here, X3. it's looking at all the other ones, while in the left-hand side you can see what we mean by a sparse connection, for example. So it's only looking at the next or the intermediate one neighbors. So it's looking at the gray marked 3. So now this particular neuron, X1, is not having all the inputs, right? So this might be a bit of a problem, but actually it's not, especially if you consider that you can combine them in different depths. So you can see this local connectivity grows the deeper you go, and this is called the receptive field of a neuron. We'll have the formula later on, but the receptive field basically describes how much of the input a particular neuron is getting inputs from. So on the left-hand side, if the kernel is only of size 3, it obviously cannot look at X1, this particular gray neuron. But if you combine enough layers, it will have a receptive field which is large enough for the whole image. All right. So I've mentioned this parameter sharing aspect. This is a bit of a terminology thing. So you call it parameter sharing or tight weights, or sometimes, somewhat rarely, but sometimes these are also called Siamese structures. Not within neural networks. You typically use the term Siamese if you have two neural networks which have the same weights, or they are called tight weights. So these are all the same when you see them at some point in a paper. But yeah, you can clearly see that just by this visual diagram that you're saving parameters, and we can go to the calculation of how much you save comes in a bit, I think. And finally, this point about equivariant representation. So here you can see what happens if you simply shift the input. You're translating this input, which is just an MNIST cipher number, around, and you can see that simply the output map is shifting, which is fairly easy to understand and makes sense, because no matter where the 4 is exactly, the outputs should be looking the same, because the output features are also encode the features at that particular location. Note that there's a star. The star is there because depending on how you implement convolutional neural networks, they're not exactly equivariant. As we'll see later, if you introduce padding, there will be some dependency on the edges of the images. So the features that you get at the edge will be slightly different, even if what is depicted is the same. So let's take a look at a very simple convolution and why it saves space. So here is a very simple example where the data is 1D. So you have a simple feature vector, which is A, B, C, D, and you're padding it with zeros. And you have a simple convolution which contains 3 elements, X, Y, and Z. Now this operation that we had earlier, the summation, you can simply write as a matrix multiplication as follows. So you basically get these striped matrices, which are called tuplets matrices. And you can see that you can store this matrix very efficiently, right? So it's simply 3 elements, and you know they occupy the diagonals, subdiagonals, and you're done. Like, you just need to save this. You can save a lot of space, and then the calculation is also fairly easy. Now for a 2D case, it looks like follows. Here, for example, the input is X on the right-hand side, and the weight matrix is W in orange. And now the matrix looks slightly more complicated, but you can also see the large white regions. And in practice, it would be, these white regions would actually be a lot more sparse, because the input would be a lot bigger than the kernel weights. For example, it would look like this. So here we now, instead of having a 3x3 input, we have a 4x4 input. So you can see the space occupied by the zeros is actually a lot larger, and the blue ones are the weights that come from the kernel. And the zeros get multiplied the more channels you have, right? So this is simply depicting one channel. Like, for example, if you have a black-white image, that would be a convolution that you run on this. But in practice, if we have RGB images or multiple channels per filter, and so you would have this multiplied in the other dimension, which you can all write in this sort of matrix in a very simple manner as well. There's another aspect which is very important for these neural networks, the pooling function. And typically what it does, it aggregates outputs. It aggregates them such that they stay local, typically, but you can also aggregate globally. So typically you have operations like max pooling, which are depicted at the bottom, where you simply take a sort of neighborhood. It's kind of like a convolution, but you cannot write it as a convolution because it's a different operation. In this case, you take this neighborhood, which you can also call kernel size, and you simply take the maximum element of each. And what you can see here is that it reduces the spatial size. So instead of having a 4x4 input, you now have a 2x2 output, which is, of course, much more efficient. And the idea of max pooling is that you simply keep the most informative elements. In practice, what you do in a lot of neural networks for image recognition is at the end, you still have a spatial extent of your neural network, and you simply do what is called global pooling. So instead of having a spatial extent like 2x2, the spatial extent is the whole feature map. So at the end, you get a one-dimensional feature vector out. And this one-dimensional feature vector, you then typically run through a fully connected layer, as we'll see in a bit. A funny idea is, for example, given this, how could you implement pooling which doesn't pool by these square areas, but how could you, for example, implement pooling which does a circle-shaped pooling? This might be food for thought. There's probably a million ways how you could implement it, but not so many ones which are efficient. So that's something to think about. But probably not super practical, but yeah. Right. Another positive aspect about this pooling is obviously that it introduces some invariance to translation. Because it doesn't matter where the 6 is. Like it could have been in the left-hand corner or further towards the top, etc. At least within some local neighborhood, it doesn't matter where it has been. So if you think about these depicting the presence of dogs' ears, etc., it wouldn't have mattered where it is. It would have still found, okay, within this neighborhood, I'm seeing an ear, and within that neighborhood, a nose, and this information would go through the network. And it's also important, especially if you have neural networks which should be able to deal with inputs of different sizes, which is very easy if you think about it. For example, if you have an image that's of size 100 by 100 pixels, then you get a certain number of outputs. And yeah, let's see. So you have your image, and then you have your convolutional layers, CNN, and then at the end, or more or less at the end, you have this feature map, which has some spatial extent, which is typically smaller, H and W, and for example, a channel dimension size of this. Now this initial H and W is typically a fraction of this. So for example, H is large H divided by 32, etc. And now you can see that the output feature map, just if you count the number of items in this, it's simply HWD. And so you can see there's an input dependency here. So what you can do is you can simply pool it for example, always to a 4x4 representation at the last layer, or you can do this global average pooling or global max pooling operation, which then leads you always to the same number of dimensions at the end, which is useful because at the end you have a fully connected layer, which then tells you all of these classes, etc. All right. So Linnet was one of the first convolutional neural networks and used for digit recognition, and also the example where backpropagation was being used for. And you can see exactly these modules being used here. So you have the pooling operation. In this case, they had a fixed pooling operation, so they wouldn't have been able to deal with a, say, 30 by 30 image or 32 by 32 image. But you can see all the elements that I just mentioned here. You have this convolution, which operates on a spatial extent. Then you have these different feature maps, and you have pooling, and so on. Now, AlexNet has pretty much the similar approach, but with some extra engineering, and we'll go into that part a bit later. Right. Let's dive a bit more into ConvNets. So I'm going to sort of, because this is such an important point, you're going to see a couple of repetitions of what we just went through, but I hope by the end of this, you'll be pretty solid in what makes a ConvNet a ConvNet. So first of all, we have, as I mentioned, the input is three-dimensional. You have the two spatial dimension and the RGB channels. If it's a black and white image, then you would have had a 2D input. The idea is to keep the structure and do something useful with it. So we're going to keep it in 3D. And 3D is not the 3D we mean by spatial, right? We simply mean spatial plus channel information, channels like colors or feature dimensions. And so this was when we had 1D vectors as inputs. We had a simple MLP. Now we're going to be working with these 3D volumes instead. So these 3D activations, they look like this, as I also just wrote on the whiteboard. You have height, width, and depth dimension. The depth dimension typically is described as number of channels. For example, a Cypher image has these following dimensions. Now, for the operation that we're going to do is the following. We had the equivalent for 1D activation. We had the following. And now we're going to do this 3D activations. So instead of looking at simply these three inputs, we're going to be looking at much more than three inputs. In this case, depending on the neighborhood size, let's say this neighborhood size is 5 by 5, and then we have three spatial dimensions. Yeah, indeed, it is 5 by 5. And we're going to add a bias term as well, because we have simple linear operations. We're still coming from the idea of simply adapting an MLP to have these shared weights. So we're still going to have this bias term. Now, let's look at how it is being computed. So the simple hidden representation, H, and that's what H stands for, is simply this linear combination of the inputs and the weights plus a bias term. And we're going to be summing across all of these three axes. What are these three axes? Again, we have the spatial dimension, we have the two spatial dimensions, and we have the channel dimension here. And all of these are simply added. And we do this for so doing this once gives you one hidden representation. Doing this twice gives you the next channel. Again, here are the sums, and you can see the difference of these being this channel dimension indicator. So for each layer that you want, or for each hidden output you get, you have a different whole set of convolutions and whole set of biases. And as a side note, this is also why these are called tensors. Tensors is simply a generalization of the term matrix. Matrix typically implies that you have two indices, like I and j. Tensors, they could have anything. So typically, we just refer to them as tensors as soon as they have more than two indices. And in this case, you can simply store the weights as tensors. Now you do this a bunch of times, and that's how you build up the depth dimension. And they basically form this column of depth times 1 by 1 by 1, or 1 by 1. And each neuron has its own 3D filter and its own bias. And if you do this and now you slide this thing across the whole feature map, then you get this box again. So you repeat this, and now you get this 3D activations. Now you get this 3D activations. And now you could be either weight sharing, which is what we do in the case of convolutions, or there's another approach. Weight sharing, it's called convolution. If you don't do weight sharing, it would be a locally connected layer, which for obvious reasons, right? But this is never used or is only of theoretical importance, really, because again, why would you want to learn something that only applies to the top left corner and doesn't apply to the bottom right corner? There might be cases, but typically you would share weights across the whole spatial extent, in which case this is called a convolution. Now, in terms of the number of channels you get, They are a lot more than input channels. So you would typically have 64 to 1,000 to even 4,000. Typically for convolutions, they gradually get deep. They gradually grow as you go deeper into the neural network, and at the same time, you would decrease the spatial extent with stuff like pooling. So the weights are four-dimensional, as I mentioned. So you have the output depth, the input depth, the kernel height, and the kernel width. Now, these, what do these things learn? So in this case, for the first layer, which deals with RGB inputs, you can actually visualize these neurons. Because they simply look at particular patterns in RGB space, you can visualize these. And they look as follows. You can clearly see some of these, and here are some activations which maximally activate these. They basically correspond to edge detectors here, and we'll have another picture later on where you can see this a bit better. In this case, for example, this neuron would be this neuron would be slid across the whole image to generate this feature map or this channel map. This neuron would be slid across the whole image to generate this one, and so on. And so that's all you get. You take each neuron, slide it across the whole image, or each convolution, slide it across the whole image, and then you get this feature map at the end. You do this multiple times, and you have a convnet, pretty much. And the only thing that you're going to add now is these nonlinearities. In the case that we typically use, we have a ReLU nonlinearity and normalization layer. All right. So let's do this. So the filters, they obviously, because they deal with the input, it needs to have the same input dimension as well, the same dimension as the input. So what we get, for example, is this, and we get this activation map, and we get these activation maps. So putting it together, we get these activation maps. Now, in convolutions, you have one parameter called the stride, which is basically by how much you move this convolution. So if you look at this, here we're sliding it by 1, which makes sense and is easy enough, but there's no reason why you want to keep this fixed. So you could instead be sliding this by a lot more than just 1. So instead, we can be sliding this by, for example, a stride of 2. So it would give you this sort of output. Note that now the output map is a bit smaller, right? So here we have only a 3x3 output map, and previously we had a 5x5 output map. Now this saves you some computation, but it might be not as accurate because now you're not computing it at every location with huge overlap, but barely at every location, for example. But this saves you some time in compute. Also, here you can see the example what happens if the stride and the convolutional kernel side doesn't exactly match the input size. So now we have set a stride of 2. So now what do? Do you stop here? That's one option. So you just simply ignore the edge. Or do you do something else? And this something else is called padding. So padding is simply you put something around the input. This input isn't only the RGB image map, but could be a feature map as well. And you could be padding this with all kinds of things. So typically you would zero pad. So that means you fill the edges with zeros. But you could equally fill it with the average value of the feature map or the pixels. Or you could fill it with reflection padding, in which case it looks like it looks like you put a mirror basically at the edge and it keeps continuing back. Yep.
Does it matter what kind of okay, so for example, if you're trying to do a max or something, you should then, for example, not take a higher value than is in the matrix? Are there like, should the output of the convolution still be the same if you include padding, or if you only look at the part of the matrix that it's actually on?
Do you mean if you need to change anything if you use padding, basically?
No, I mean if you so here for example, if you would use zeros and you calculate the max, then it doesn't change it because
yeah, that is true. Yeah,
the max won't be in
yes.
the pads. But if you use average, then it would change
Yes.
the output. So does that matter?
Yes, that matters. And that's why you have these different padding types. Yeah, exactly. A simple convolution would also change the value, right? Because it simply adds stuff together. Now this stuff is just 0, so it will be less, potentially at least. I mean, feature maps can have negative values, so at least for the input, well, inputs can also have negative values because you can normalize them typically. But so yeah, it does matter. Yeah.
Okay. So you should try to keep it the same.
Yeah, and you should typically simply use whatever is standard again. But yeah, there's another question.
Once we got on all the activation maps, so after applying all the filters, do we apply the activation function reloop? Is this how it works?
Yeah, so you would, yeah, exactly. So you get you slide every filter across the whole image, then you get these activation maps, and then you would apply a nonlinearity. So we're still simply, what we're essentially doing still is basically f of ax plus b, except that this is now has some structure.
Then reloop would be applied on each cell of the feature map?
Everywhere, just on each, yeah. So it doesn't look at neighborhoods, it's simply element-wise operation. Yeah. And actually, ReLU is very efficient, right? Because if you remember how floating point values are stored, you have the sign, the first bit stores the sign, and the rest stores like the mantissa and the value, and you can simply check, okay, is the sign negative? Then throw it away, then set it to 0. So it's quite efficient, actually. Any other questions? All right. So yeah, this padding, something to note here. Now, I mentioned this, that you can actually compute this. So in general, you can compute the output size as follows. So you have the input size, Win, and then you have the padding, the amount of padding you're using, and it doesn't matter, obviously, what kind of value you're using here, minus the kernel size, and S is here the stride. And then you add +1. And you do this, these half brackets, which means you round down if you're getting a value which is non-integer. So in the case of these values, for example, k equals 3, stride equals 1, padding equals 1, you actually get this sort of magical formula that the output map will be the same size as the input map. And this is actually what has been used in the neural network VGG, which basically only consists of filters of this shape. Note also that here the input size is the same as output size, which means you can stack these things as long as you want. If the output size is smaller than the input size, at some point you're trying to, let's say, apply a 4x4 filter on a 3x3 kernel map, which will throw you an error, which there's simply no way you can do this. So you need to be a bit careful about that. And sometimes this can happen if you're not very careful. In which case, yeah, if you have that thing happening, then you might want to pad it or apply smaller convolutions, for example. All right, I think we're gonna take a break here, and then we're gonna continue with 1x1 convolutions. All right, let's get started again. All right. Now let's talk about another cool type of convolution. We're going to talk about the one-by-one convolutions. Thanks. All right, the one-by-one convolutions. So the simple description is the following. Well, first of all, if you hear one-by-one convolution, what does it mean? It means the kernel size is simply of spatial extent 1. So the height and the width of the convolution are 1. So for two-dimensional signals, this doesn't really make sense. Homework, why? But for ConvNets, this does make sense because you need to remember we are operating over three-dimensional volumes, and the filters always extend through the full depth of the input volume. So for example, if the input is 32 by 32 and 3 channels, then doing one-by-one convolutions would be doing three-dimensional dot products and mixing the input channels, input information across channels at every single spatial location. So if you're doing a one-by-one convolution, you know exactly what the spatial output size will be. Well, it will be 32 by 32. And then it simply depends on what kind of output dimensionality you're giving the one-by-one convolution. For example, if you say it's 64, then the output will be 32 by 32 by 64, which will now have 64 channels. Why would we ever want to do that? We just learned convolutions are a great way to have something that sort of looks at an area, can detect edges and so on. Well, the first thing is that one-by-one convolutions still have the one main benefit of convolutions, which is this weight sharing. You're still applying one operation across the whole image, right? But you're not doing it spatially now. Instead, you're doing it across channels. And this is very good because of the following. It's a very cheap method computationally. For example, take a look at this thing. So you want to go from a 28 by 28 by 192 feature map. So it has a spatial extent of 28 by 28 and 192 channels. You want to go to this 24 by 24 by 32 feature map. So typically, if you want to do this normally, you can, for example, apply a 5 by 5 convolution, which has an output dimensionality of 32, and you end up exactly at this 24 by 24 times 32 feature map. And you can simply calculate the number of operations that you need to do, and you end up at around 120 million. It's not a lot for neural networks, it's not a lot for computers, but these things stack up. And now let's compare what happens if we use a one-by-one convolution. We can use it in the following manner. So we first take this and simply project the 192 feature map to a 16-dimensional feature map. And now in this much less deep feature map, you can now apply this 5 by 5 convolution. So you're still looking at the spatial regions of a 5 by 5 convolution, which you, as before, but except now you're decreasing the depth by a lot. And this is a lot more efficient. So you can see here, now the calculation merely ends up at 12 million. So you're saving 90%. You're just computing 10% of the operations of the above case. Why is this the case? Because 5 by 5 convolutions, even though they look so innocent at the top, they actually have, you can calculate exactly how many weights they have, right? So 5 by 5 convolutions, so obviously they have this spatial extent, right? So this is 5 by 5. And then they need to take care of the input size, which is, in this case, 192. So let's go in this direction. And now now it's going to be a bit difficult to depict. So they have 192. For each input channel, they have a different set of 5 by 5 filters, right? And they need to, per output, they have that. So you have a ton of values. And And this is obviously magnified by this 5x5 convolution. So if you instead first reduce the channels and then apply this, you'll get a lot of benefits. Yeah?
So in the first one,
Yeah.
we go directly from the depth of 192.
Yes.
For the other one, we have a middle step.
Yeah. Yes.
Do we lose information?
Depends on how you do it. If you reduce it down to 1, you will lose information, for example. So there's some engineering going on, yeah. So it's not the universal solution for everything, yeah. And sometimes these operations are also called bottlenecks for the obvious reason that you're sort of compressing it to a lower dimensional representation. And yeah, yes?
Is the dimensionality just completely random, or is there a certain reason you scaled it down lower and then upscaled it again in the next step?
Yes, there's a reason. For example, if you can also apply a one by one convolution with the same input channels as the output channels, right? That simply does mix the channel and mixes it in the same manner, but then obviously the 5x5 convolution isn't saving anything. So you need to project it into a lower dimensional space in order to get any savings. Right, I mean, if you think the 1x1 convolution could have equally given you a 28 by 28 by 192 output.
Not that much
Yeah.
if you go more to the 32.
Yeah, you can, at some point there will be an equal amount, yeah.
Yeah, because you go lower than you actually wanted.
Yeah, this is just an example. Yeah, yes.
So you mentioned that if you put it like until one dimension, you might lose some information, of course. So is there some kind of rule that says like how many dimensions should be bottleneck?
So this is sort of the stuff that has been found by graduate student descent, right? So this has been like lots of PhD students, lots of researchers trying out these sort of architectures in different manners and figuring out what works best. There's also methods which try to automatically find what works best, which are extremely computationally expensive, but there's no rule that says it always needs to be. Like you can kind of sometimes have a feeling of it, like typically for large-scale images, probably 32 seems like very little, whereas for like very low-dimensional images like MNIST ciphers, that's probably enough, but that's just, yeah. And you would typically find these sort of things in neural network implementation. So you can very easily look that up and take a look at these. So regarding these 1x1 convolutions, I want you to discuss with your neighbor, just 3 minutes or so, what the difference of a 1x1 convolution is to a fully connected layer. And B, when are these 1x1 convolutions good and when are they actually not so useful? So please turn to your neighbor or neighbors if you're if you're in a sparse neighborhood, and yeah. All right. All right. Anybody want to tell me some reasons when a one-by-one convolution is not so good? Any volunteers? No? Yes?
Equivariance.
Equivariance? Can you elaborate a bit?
It's probably not equivariant, or it doesn't allow for equivariance. So if that matters, then it will mix the channels too much, and like if important information will get lost.
Okay, so equivariance, I think we had earlier in the slide that if you slide the input, right, then the features also slide. Actually, you have the same here. So one-by-one convolutions, they're still applied spatially, right? The only thing they are doing is mixing the inputs between the channels. So they would keep everything still as equivariant as it was before. But thanks, yes?
I mean, that's quite abstract, but if those 192 dimensions carry a lot of different information that cannot be compressed into a lower dimensionality, it's not good, but if it's the 192 dimensions are somewhat redundant, we could compress them.
Mm-hmm. Yes, yes. So the point about we need to be careful when to compress and when not, which we don't really know exactly. I mean, actually, one thing that you might have seen in Machine Learning 1 is this PCA analysis. So you can simply look at the number of relevant factors, and at some point you might see, okay, there's only, like effectively your data only has 10 dimensions, so probably 10 might be a good idea, so that might give you some indications.
Does
Yes?
it somehow behave like a PCA, by the way, this compression? Does it somehow learn like the most important shared dimensionality in the dot product?
It pretty much will, yeah, I think so. You can actually probably do the mathematics that for like a single hidden layer, it probably will do that, but you don't have any guarantees, so yeah. Because, yeah, PCA is also just a linear combination of inputs. This is just a linear combination of inputs as well. All right, moving on. Another factor that we haven't touched so far is dilated convolutions. So in the first case, we had this convolution where you're simply applying a 3x3 filter on an image. You can actually give some holes. So you just dilute this convolution, so to say. And now you can see it's covering a lot more space. Of course, now there's some white space in between, so it's not ideal. But this way you can basically deal with much larger images much quicker. So you still have this thing where the receptive field grows pretty quickly if the deeper you go into a neural network. And once you add dilutions, it will grow even quicker. And so you can deal with much larger images. For example, for object recognition, object detection, where you have an image and you're trying to detect small stuff, you're not dealing with 32 by 32 images, but often like 1,000 by 1,000 images. And so you multiply that by the channel dimensions of neural networks, you get to really large volumes. And so if you want to not have them too deep, or if you want to have them deal with it efficiently, often dilated convolutions are used. Yes?
Would this be equivalent to, for example, having a large stride and then doing convolutional?
It is not equivalent, right? Because now these things are looking sort of at this checkerboard pattern thing, whereas a stride can really look at connected things. So it's slightly different, but they have the same effect. So what you want to use, like if you want to have a larger stride, or if you instead want to use dilated convolutions, sort of depends on whatever applications you have. Yeah. Right, we mentioned this pooling. So max operation is quite common. Average pooling is also quite common, I should say. But sometimes average pooling might be a poor choice. So you can see this in this image. So here you can see some activation simply from one neuron, and there's some input image, and we've taken this one neuron's activations and visualized these. They're somewhere between 0 and 1, let's say, and you have an image which is between 0 and 1. And if you do max pooling, you can clearly see the structure is almost enhanced or almost sharpened, while you have now a smaller spatial dimensionality. That's why if you instead think about average pooling, this might be a poor choice in this case. If you're doing recognition where you simply want to detect the presence of something very salient. However, average pooling is quite often used at the end of a neural network, where you want to get to this point where you simply want to have something that's of dimensionality d, where you can then apply a fully connected layer. So if you look at ResNets, for example, or even AlexNet, which we're going to look at now, you nowadays have an average pooling layer at the end. So yeah, we had this. And the visualization for maxprop is here. And yeah, the backprop rule you can also find here. And similar to why we need pooling or why we use pooling, this thing about reducing the spatial extent, you can also use the stride and the dilated convolutions as well. And pooling layers sometimes can be quite problematic because they get rid of a lot of information. For example, in GANs and VAEs, quite often they're actually not used, but instead these sort of operations are used. Yes?
What is if you want to detect something that's very dark? Isn't that the less pooling doing the opposite of what you want?
So if you're trying to detect something very dark, if your data set is very dark, you're still normalizing it back to 0 and 1. So all the contrasts, basically your input data set will be as bright as a normal data set. Of course, that's not to say like there's special methods which deal with dark scenes, for example. But yeah, because cameras also operate differently in the dark. So there's some specialized methods which can deal with this a bit better. But typically, yeah, you would have, for example, a much lower mean that you subtract. And then you still end up at 0, 1. Yes?
So there's this, maybe I missed this for the second point, the starting pooling layers has been found the giant model. Why is that? Is that because we're just not losing information? Or?
Yeah, that empirical observation, but that probably is the reason, yes. Also, we've sort of gotten rid of pooling in isotropic models, which are basically models which keep the same spatial size across layers, as we'll see in lecture 7. So one example ConvNet is the following. So you can here see a couple of layers. So what are we visualizing here? We know all the activations are multidimensional, right? So each volume of activations along the processing path is here shown as a column. And because it's difficult to visualize these 3D volumes, we lay out each volume slices in rows. So you can basically see what's happening throughout the neural network here. So you have, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 convolutions, and 10 convolutions each. And it's a not so very deep neural network. And you have these pooling operations going on. The pooling operations also, you can clearly see how the spatial extent is decreasing. So technically, these last representations would be much smaller. We're just visualizing them bigger. That's why you can see these artifacts. And finally, you have this fully connected layer, which simply connects all the inputs, all the preceding inputs to make this final prediction. And in this case, yeah, it's these 10 conv layers, 3 by 3, with 2 by 2 pooling filters. All right, so now I want you to think back about fully connected layers and convolutional layers and tell me which statement is true. Fully connected layers are a special case of convolutional layers, or convolutional layers are a special case of fully connected layers. And by special case here, I mean it can be recovered by the corresponding settings. For example, if you call a programming language for neural networks like PyTorch or TensorFlow or Keras, can you make a thing fc equals conv with some settings, or can you make a conv equals fc with some settings, basically? All right. It's a binary choice, so 50-50. All right. 3, 2, 1. Ones and twos. Ones, a bit more ones. Some twos. All right, so the answer to this question, and I think you like discrete answers, so I'm going to say the answer is 1, but 2 is not bad. So the reason for this is the following, right? So the reason why 2 is not bad, first of all, is we saw this, right? This is a linear layer, and in the case of a fully connected layer, this matrix has all the entries, right? We had this. And in the case of a convolutional layer, it only has entries which sort of look like this, right? So in a way, conv layers are a special case of fully connected layers, but, and that's why I added this special case definition, if you have a input which is, for example, 28, 28, 3, how can you approximate a fully connected layer? Well, you simply implement a conv which has input size 3 and kernel size 28 by 28, and then whatever output dimension. This is equivalent to a fully connected layer that takes all this input, right? This is equivalent to a fully connected layer which takes 28 by 28 by 3 and goes to dimensionality D. Can everyone see why? I hope it's clear. So the number of, these are simply the number of connections, right? And if the filter size is as big as this one, and it's applied across all the channels, well, then it's exactly equivalent to what a fully connected layer is doing. Good. All right. Now a quick intermezzo of how research gets done. So in the previous parts, we had get a fundamental understanding, read some papers, including how to read papers and implement and tinker with code. So today, I want to encourage you to be curious, and be curious with the following statement. The most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka, but that's funny, from Isaac Asimov. He's obviously, he's one of the biggest sci-fi authors out there and was really interested in science in general. And I think this one's a very good one. Because whenever there's a that's funny, that means there's a delta between what's expected versus what is being observed. And for this, first of all, you need to trust your experiment and understand the broader context to form an expectation, right? There's this delta that you have, this incongruity, which is also quite often explained why jokes are funny. You have some context, but something happens that you didn't expect. And for this, obviously, you need to understand what is to be expected, right? So you need to have this fundamental understanding, and you need to be able to trust your experiment and not say, okay, if it's a bug, then it's probably not very funny, right? And then you're not finding something that might be interesting. And also, you heard from Hubel and Wiesel, these two Nobel laureates earlier, right? So as they weren't getting any signal, but only when they were accidentally sort of trying to slip this thing out of the microscope did they get a signal. So that's literally their that's funny moment. Yeah, as I said, for this, quite often you need to be able to see what the context is and also trust what you're seeing and hold that contrast for a while. So the advice for today is don't ignore this moment. Instead, follow this up by what I call structured tinkering, which will be the next part. So science sort of gets done like this. What's the opposite of eureka? Yeah. All right. So moving on. Next, we're going to look at a case study. We're going to dissect this AlexNet a bit. Remember AlexNet? That was the neural network that sort of heralded in the deep learning era. And this is the diagram of AlexNet. It consists of 8 layers. 5 of them are convolutional. 3 are fully connected. AlexNet has a ReLU nonlinearity, which back then replaced the tan-h function. It was run on 2 GPUs. It had local response normalization and overlapping pooling. We're going to talk about each of these points in turn. Activation function. Here they made a plot which shows that ReLU trains a lot faster. So here you can see the training error rate on the left-hand side, on the y-axis, versus the tan-h. So you can see ReLU trains a lot better. It's attributed to the fact that tan-h sort of, you have this saturating behavior at some point, versus ReLU. It's simply, once you're in the positive, it doesn't saturate at all. So it's fairly quick to train. So you have, after every convolution operation, you have this ReLU layer. As I mentioned earlier, this is very fast to implement as well. And training with multiple GPUs, how they did it is using the group convolutions from last time. So they had basically half of the neurons of a certain layer on one GPU and the other half on the other GPU. And the GPUs communicated between themselves after each layer. And this allowed them to increase the computation, the model size. And you need to remember back then, they had no PyTorch, no Caffe, no Torch. They had to do everything manually on CUDA, and GPUs had like, I think, only 3,000 megabytes of memory. So it was extremely difficult back then. But this did lead to an improvement. And the inter-GPU connections are here. And on that note, I want to talk briefly about communicating between GPUs and PyTorch, as it's very likely that some, if not all of you, will at some point be running stuff on multiple GPUs. And there's a couple of approaches to how you do this. So I should first say the most common thing at the moment is what PyTorch calls distributed data parallel, which means the data is parallelized across GPUs. AlexNet was basically model parallel, right? It had some neural network layers on one GPU and some on another GPU. While distributed data parallel, the standard at the moment, is where you have on one GPU each, you have the same model on each GPU, and you're simply spreading the batches. I think we had that last time as well. And in the backward mode, you sync all the gradients across the GPUs, and you sync them with an operation called all reduce. All reduce simply accumulates all the gradients, and rank now is the same as GPU number, basically. So GPU 0 has rank 0, and so on. And now every GPU gets all the gradients from every other GPU, sums them up, and because a sum, well, every time you sum these elements together, you get the same. So at each GPU, you get the same gradients. So you can simply update the weights locally, because you know the gradients that you've summed up, they will add to the same gradients at every component, at every GPU. Besides this all reduce operation, there's other operations for distributed computations. So I made them here, but you can look them up on this PyTorch distributed overview. But these would be, for example, not only all reduce, but they could be scatter. So instead of getting all the activations from all the GPUs, you can send from one GPU, you can send it to all the GPUs. And yeah, you have a bunch of operations that you can use. All right. Moving on to this normalization that AlexNet introduced. It's called local response normalization, and it looks as follows. First of all, nowadays it's mostly replaced with batch norm or layer norm. The main idea back then was actually motivated by neuroscience. And here I indicates the filter. So I is the index for the filter. A and B are the pixel values before and after normalization. And N is the total number of channels. The rest, K, alpha, beta, eta, are hyperparameters. And K is simply used to avoid singularities. So in the case of, it's simply the epsilon parameter for Adam, because if this sum ends up 0, then you would be dividing by 0, which will throw you errors. So you need K to be some value. Alpha is a normalization constant, and beta is this sort of contrasting constant. The idea was basically that you add a local contrast between channels. Later it was also made to be spatially, so you have this intra-channel layer norm, local response normalization. And the idea is to enhance the peaks and dampen the flats in responses in the feature map. But this is nowadays not used anymore and is fairly expensive to compute. All right. The next step they introduced was actually something we haven't talked about, which is overlapping pooling. So I mentioned you can increase the stride, or you can decrease it as well. So you can, for example, have overlapping pooling, which means you end up with a feature map which has more values. So you're not having a very strong decrease in the spatial dimensions. So you had these overlapping poolings at these locations, max pooling, max pooling, max pooling, all with strides, or strides which were smaller than the kernel size. And finally, we have the convolutions here, operating here. Note that the first convolutions were pretty large at 11 by 11 pixels. And the overall network has 60 million parameters. Be careful, there's actually 2 versions of AlexNet because the authors submitted one paper at some point, and I think half a year later they submitted a slightly different version of it. So whenever you use AlexNet, be slightly mindful of that. And they also back then used data augmentations like translations and horizontal reflections and some changes in RGB intensity values. At the last layer, they also used dropout because the last layer, as you can see, is like 2,000 dimensional. Well, if you combine it across the GPUs, it's 4,000 dimensional, and you have 2 of them, so that's quite a lot of parameters. So dropout was a very good way to regularize this. The learned, yeah?
Just a question, why would you need translational data augmentation if you're using convolutional network? Is the whole point that we get that for free with their covariance?
It's a good point. That's the point about neural networks are sort of translation invariant. You have all these issues with padding. So we'll see some actual results of translation invariance or how invariant they are in a bit. The learned filters look like the following. So at the top you have the filters that were learned on one GPU, and at the bottom on another GPU. Have a think about why you have this sort of specializing behavior going on. So why does one GPU mostly learn these edge detectors, and the second GPU mostly learns these like color contrasts or color blobs? So what you can see, for example, in the bottom row, all the way to the right, at the top part, so third row from the bottom, you have this green blob, right? So this neuron will fire most strongly if there's a green blob present, just like the top parts mostly activate when there's such an edge present. So have a think about it. We can talk about it next time. The main idea is because of these grouped convolutions, because these things, that's how they specialize, but yeah. All right. So we can do some ablations. So for example, we can remove the layer 7 with the dropout, and you only get a 1% drop in performance, but you have 16 million less parameters. 16 million, that's this 4K by 4K fully connected layer, right? 4,000 by 4,000 ends up at 16 million. So that's how you get to this number. And you get a pretty mild drop in performance. So that's pretty great. You can also drop this last layer, this fully connected layer, and then you end up with a slightly larger drop, but hey, you save a lot in parameters. This won't win you any competitions because now you're suddenly like below the other teams or below the other models' performances, but this is pretty good. As a matter of fact, this has been done quite like for efficient neural networks. However, now you need to be a bit smart about how you can get from these convolutional maps like this, how you can get from here to here. And the way you do this is simply by having this D already be the same size as what you want to eventually end up. So if, for example, you're categorizing 1,000 classes, 1K, then instead of having this fully connected layer do this 1,000, you can already set the convolution to only give you a 1,000 dimensional feature map out. And then you simply do this pooling operation, and then you also end up with a d-dimensional output, right? After pooling, after spatial pooling, you get a d-dimensional vector, which, you can straight use the loss for that. So you're sort of abusing a conv layer to do the stuff that a linear layer would be doing. Yes?
You can also use the equivalence thing, right? To have convolution.
Yeah, you can add a 1-by-1 convolution. It would be more efficient. They weren't around back then, but you can also cross some mid-level convolutions. Importantly, once you start crossing too many, then you have a pretty shallow neural network and it won't be performing well anymore. I mentioned this translation invariance. Here you can see on the y-axis, you can see the probability of the true class being predicted for a couple of images that are depicted on the left. So you can see, first of all, by only vertically translating the image, you can see the probability of the true class actually varies quite a bit. Now for the lawnmower, it doesn't vary too much, so it's pretty stable up until at some point one lawnmower, I think, starts disappearing from the image. For others, you have quite some irregular zigzag stuff going on. And that's also a reason why people have actually been working on designing neural networks which are exactly translation invariant, which are exactly equivariant. And this is also like one of the specialties of AMLab, which is a research group here. Scale invariance also, these neural networks have to some degree. So in this case, the starting point is not all the way in the middle, but is actually at 1.0, and now you're zooming in, basically. And you can see it also stays fairly stable, but is also not exactly how you would want it, right? So some classes drop pretty quickly, some don't. You can see a similar thing for rotations. Actually here for rotations, you can see this funny behavior of peaks at, you guessed it, multiples of 90 degrees. Because in the natural data set, there will be some images which have been shot at 90 degrees. So for these, it will work fine. And for everything in between, it pretty much doesn't get it. It simply is out of distribution for the model. It cannot handle it. I recommend some further reading if you want to understand what these neural networks are learning. Like I mentioned, we've looked at the filter 1 of AlexNet. This pretty much learns these edges and blobs. And here they really look into more detail. Okay, what do the deeper layers learn? And how do these different edges, for example, get combined to learn more difficult features, etc.? Yes?
Is that within 90 degrees spikes, is that worthy because the images are shot in this, or because the convolutions can be learned with 90 degrees rotations invariant? Like you can replace them only with, get what I mean? Like you can learn them in a 90-degree shift.
You could? Yeah, you could learn them. So if your training data also has 90-degree rotated examples, you'll probably learn that, okay, these filters I can use when the image is rotated, these filters I can use when it's not rotated. But every filter is always applied in one manner, right? So, but you're right, like for example, the main idea of equivariant neural network is that you have a filter, but you apply it in different manners, the same weights, but different manners. All right? So let's talk about transfer learning. So the idea of transfer learning is that you can transfer the learnings from a large data set to a small one. So in this case, for example, from ImageNet to my data set, which say your company, you have 1,000 images, you want to solve some task. So you have these two data sets, target and source. In this case, for example, ImageNet, fully annotated, plenty of images. You can build a model. And then you want to use the data set T, which, for example, doesn't have that much annotation, has much fewer images. And the annotations or the input, the content of the two data sets could overlap, but they don't need to. For example, my data set could be a medical data set or satellite images or whatever. And the main idea of transfer learning is that we can use the model HS to learn a better targeted specialized model HT. This is called transfer learning, and I'll give you the update for today. So today, dataset S is typically huge, and by huge we mean something like 5 billion. And we can build a model HS because it's not annotated. We would typically use something like self-supervised learning because self-supervised learning doesn't rely on annotations. And these models truly benefit from this large scale. So they will have seen a lot more images. They will have seen all the rotated dogs in the world, for example, if that's something you care about. And will be able to generalize a lot better. And likely, the larger your data set is, the more you have a probability that your target data set actually is a subset of that, which is great. But also, the larger your data set is, the better representations you can actually learn, the better models you can actually learn. So it's easy for these edge detectors to say, okay, these edge detectors are all you need. But for the deeper features, they are much less robust. So you already saw that the probability of the right class flips quite quickly and doesn't stay stable at all if you translate a bit. And it's even worse if you start introducing some noise and so on, as you'll see in the second assignment. All right, so reason for transfer learning is here, and it's not just the case for CNNs, but also for vision transformers. And typically you would use, if you were ever to do it yourself for like a case, you would typically download existing pre-trained weights, which you can find, for example, on PyTorch. They're very good at transfer learning. Generally they're very good at transfer learning. And there's two main solutions. So you can fine-tune your neural network, or you can simply use it as a feature extractor, just like we said, I think on the second lecture, where we simply treat the neural network as a nonlinear feature generator, and then we have a linear layer that does the classification, essentially. All right, let's talk about solution one. We fine-tune HT using HS as initialization. So we basically assume that the pre-trained parameters give you a good initial solution. So now you're initializing neural network, not by random weights, but instead by the last checkpoint that you got on your source data set. So basically, it looks like follows. So you simply set them like this. And but of course, now the question is, okay, do you initialize all of them, or do you only initialize a few? The case where you initialize all of them, but leave the last one randomly initialized is the case where which we're going to talk about as solution 2, which is you treat them as a nonlinear feature extractor. All right, so the classifier and loss. The loss layer is essentially is what gives you the classifier. And so if you have the same labels, you can literally keep the classifier label the same, right? But if you have different labels, say if you're moving from 100-way classification to 10-way or to 500-way, you cannot do anything with this layer, so you need to reinitialize it, which is easy enough. Fully connected layers, obviously, because they're towards the end of the neural network, they are what basically combine all of these features that you get from the convolutional layers, so they're extremely important. And they are also the ones that specialize. So we saw, for example, Conv1, first convolutional layer, they just learn edges. They are not very specialized. Edges are useful for medical images, for satellite images, for all kinds of images. But the further up you go the hierarchy, the more specialized you will be. And in fact, for AlexNet, in, for example, FC7 and FC8, you can really find a neuron which activates at snouts for dogs, for example, or at hot air balloons. And you can visualize these neurons as is done in these blog posts that are recommended. Right. You can also initialize these upper convolutional layers. That is, for example, some mid-level features. If your data set is slightly further away, then it's recommended to also to retrain these, but only if your data set is big enough. The lower convolutional layers, they capture this low-level information. You typically don't need to fine-tune them unless you have a large difference. So if your data is suddenly at night versus at day, then probably it's good. So the summary is kind of, okay, retrain these parts depending on this sort of data sets, which is described here. There's also, because if you reinitialize something, but the rest is already trained, you will have to have mixed learning rates for your neural network. So typically, you would divide the learning rate that you use for adaptation. You would, the layers that were initialized in a good manner, you can use a lower learning rate, but the newly initialized ones, which are still random, you would use a much higher learning rate. All right. Yeah, so if you have enough, if your data set is enough, you can fine-tune all the layers, of course. But there are some disadvantages with fine-tuning all of them. It makes your model basically only specialized to this particular data set, and it might overfit to that one as well, which has implications on robustness. For example, if your pre-trained model gave you a lot of good robustness results, and now you're fine-tuning on a really small data set, it might easily forget all of these robustness. As a fun note that you can also just learn the normalization layers in the case of batch norm, which has parameters. Right, so the case as a feature extractor is similar, but you only train the last layer. So you're essentially using the neural network as a pre-trained feature extractor, and this is a common approach to measure how good representations are. We're going to be talking more about this in the self-supervised learning lecture, because it's all about measuring how good representations are. But this approach also generalizes to other useful things. So if you're a company and you need to deal with images, you might just want to not have one neural network for each task you're doing, but simply have a pre-trained neural network which gives you some generic visual features, and you save them instead of an image, for example, and then you have some networks which do something with these visual features. Yes?
Might be off topic. I think companies have a lot of commercial interest in pre-trained networks. Is there any copyright or any marketplace for pre-trained networks?
Yeah, it's slightly off topic, but it's a good point. ImageNet, for example, the one that's the most common pre-trained one, actually excludes commercial use. There are some other data sets which allow commercial use. It really depends on that stuff. Yeah. But still, probably every company uses ImageNet, but anyways. Or at least every startup. I think depending on the company, they won't take the risk, but yeah. All right, and about these benchmarking techniques and how to measure how good a linear layer is, we'll talk about in the self-supervised learning lecture. And with that, thanks, and yeah, now 15-minute break, and then we have the tutorial with Philip. Mm-hmm.
I think you don't need flipped images, because you could, let's say there was the original image, have here the convolution,